When you think of virtual reality, you probably imagine a bulky head-mounted display, right? Most of us think of devices like the Oculus Rift, or HTC Vive, or even the Apple Vision Pro that completely immerse you in a digital world by placing images right in front of your eyes. But what if you could experience VR without wearing a headset at all? This idea isn't entirely new. In the early days of VR research, headsetless systems emerged as an alternative. One of the most famous examples is the Cave, or Cave Automatic Virtual Environment, developed in the early 1990s. In a cave, images are projected onto the walls of a room, so you're enveloped by a virtual world without wearing any head-mounted display. Another example comes from Johnny Lee in 2007, who showed that you could turn a standard TV into a window-like virtual space. As cool as these systems are, there's one big problem they share in common. They're not actually headsetless. You see, in order to create an image with the right perspective, you need to know the position of the user's eyes in 3D space. And currently, these systems require the user to wear a pair of glasses with infrared markers to track their movement, effectively turning them back into a headset-based system. Enter human pose estimation. In recent years, advances in computer vision and deep learning have made it possible to accurately detect key points on a person's face and body in real time. This means, in theory, we can determine the position of your eyes without requiring any extra hardware on your face at all. My project, Virtual Window, explores precisely this possibility. The question I wanted to answer was, can we use human pose estimation to create a headsetless VR display that works as well, or even better, than a traditional marker-based tracking system? In this video, I'll briefly demonstrate the marker-based and markerless tracking systems I built to conduct this investigation. My markerless tracking system was composed of 2 cameras. Using Python, I applied Google's MediaPipe pose estimation model to estimate the pose. From this, I extracted the eye position and used stereo depth estimation to calculate my perspective in 3D space. For the marker-based system, I used the same cameras as before, only this time with infrared pass filters attached that block any visible light. This way, I could attach an infrared LED to a pair of glasses and turn it into a tracking marker to easily find my visual perspective within the image. The code implementation for this method is much simpler. I first apply a Gaussian blur to remove any noise from the image. Next, I simply search the image for the brightest pixel, ignoring anything below a certain minimum threshold. As before, I use stereo depth estimation to convert these pixel values into 3D coordinates. Both systems were integrated into Unreal Engine 5, which receives the tracking data and renders a virtual environment with the correct perspective shift to a large screen. Now for the results. Here you can see the marker-based tracking approach in action. Due to the relatively low computational cost of tracking the marker, this approach has lower latency and higher frame rates and is generally more accurate. However, there are occasional tracking errors due to background sources of infrared interference, as can be seen here. And errors also occur if the LED is blocked from the view of the cameras, making it vulnerable to occlusion. This can be a problem if multiple people are using the same space, as demonstrated here by my lovely assistant. Although the system succeeds in tracking my visual perspective, the glasses can be quite uncomfortable, especially for users who already wear their own prescription glasses. Here's a first-person perspective of the marker-based tracking system in action. Next up, we have the markerless tracking system. Right off the bat, you'll notice this method has a lower frame rate than the marker-based system, reflecting the higher computational cost of performing pose estimation on 2 camera inputs in real time. Nevertheless, this system is significantly more comfortable to use, and it has a strangely smooth and natural quality to the tracking. One major downside of this system is that it can be confused when multiple people are in the camera view, as each camera may start tracking a different person than the other, causing errors in the perspective shift. But as long as it's only used by one person, this approach actually outperforms the marker-based approach in its robustness to object occlusion. By tracking the entire pose of the user, it can make guesses as to where the user's eyes are, even when they're not directly visible. Here you can see the markerless tracking system taken from my perspective. User feedback showed a strong preference for the markerless system, performing as well or better across all usability metrics, despite performing worse on a technical level. This suggests that human experience favors a more organic interaction over merely objective performance. Despite neither system being at the cutting edge of tracking technology, I believe this work has offered a fair comparison of both methods under equivalent resource constraints. Future developments could address the current limitations of our markerless approach, such as using feature extraction to distinguish between people in the scene. It would also be fairly easy to include the addition of hand and leg tracking for system interaction. This project has been a valuable learning experience for me, and I'm excited to see how this technology might develop in the future. Many thanks to Dr. Robin Hill for supervising me over the course of my dissertation. I hope this video has been informative, and thank you for watching.